Hello, I'm Josh Bearden,
Dennis Trent.
and today we are presenting our final project from the University of Nebraska Lincoln School of Computing class, Numerical Analysis. Our project is over the CPU and GPU transistor count and analysis, and we'll hop into it. So, to begin with our motivations, both of us are interested in the hardware and the hardware industry, so we decided to go with this topic. And so a few details to begin. Processing power apparently is growing exponentially over time. And this is with CPUs, computer processing units, and GPUs, graphics processing units, as well as many other semiconductor units that are partially considered in this study. Technology seems to advance rather quickly over time, and to focus for our data set, we used CPU versus GPU performance. We'll also be comparing our analysis with Moore's law, which is a study of exponential growth in the hardware processing power.
All right, so a little bit on Moore's law, just a little bit of background. It was first proposed by Gordon Moore from Intel. He was one of the co-founders of it, and this was one of his observations or predictions on computer chips and hardware. Basically, it entails that the number of transistors in computer chips will double once every 1 to 2 years, give or take. This is due to better manufacturing, smaller component sizes, and even higher chip densities. Some say, however, that Moore's law is deteriorating. One of these is NVIDIA CEO Jensen Huang. A bunch of others. We'll study through this slide just to see how that actually holds up.
And so here, this link provides the data we used. It's compiled into a table of many companies, many different products from the year, and we used from 1982 to 2020. The data from CPU manufacturers, Intel, Texas Instruments, Toshiba, and all that, as well as GPU manufacturers, NVIDIA, AMD, Samsung. We decided to take the average number of transistors in every product for a given year and average those transistor counts to a single data point for a given year, so that we only have one data point per year, 1982 to 2020. Also, as is reflected in our data, there were no discrete GPUs until 1999, so any graphics integrated or any graphics present were integrated in the microprocessors already existing. And for the purpose of the study, we decided to remove the data from every other year and interpolate the values that would be those years, and then compare those to the actual year data that we had.
All right, so a little bit on the methods that we used. First, we used the natural cubic spline interpolation. This is done through the MATLAB spline function. The other one is the piecewise quadratic interpolation. This is one that we wrote ourselves, and you'll see the implementation later. And then the exponential regression using MATLAB's curve fitting app. This is used to represent Moore's law, and we can compare our data to that. So a little bit on the natural cubic spline interpolation. We've done this through the lectures, so I guess we won't be spending too much time on this, but.
And same thing here. These equations were provided during the lecture. You can pause the video and check these out at your leisure.
All right, so to start off with the natural cubic spline interpolation, these are the results for our CPU. You can see on the graph the interpolated values in blue and the original data set in red. One thing to note is that a lot of the original data point has large spikes in the data. It's got peaks and valleys here and there. And you'll see that the cubic spline interpolation really attempts to smooth that out and sort of normalize that quite a bit. So a bit of error from the natural cubic spline interpolation for the CPU. The RMSE value we found was 1,186, and our average percent error was about 54.5%-ish. You'll notice that these values are kind of high, or rather really high, but we can attribute that to possibly because exponential data and because the data seems to be fluctuating heavily, that the natural cubic spline seems to find trouble keeping up. Some more results for the GPU, natural cubic spline interpolation. As we explained more from the earlier slide about the data points, there's no discrete GPU chips before around 1999-ish or 94. So you'll see that in the data set, there are no points in those spots. Again, with our interpolation though, there are some spikes in some different data points that are quite off from the line, and you'll see that the natural cubic spline attempts to normalize that. Again, with the GPU, we found our error to be about RMSE 3,930-ish. This is again really high. It's even higher, almost 4,000, which is higher than the 1,000-ish we found from CPU. And our average percent error is actually lower here, which is interesting, but the relative error is going to be about 47.65%. And here you can see the table for the different points we had that were interpolated and their percent errors.
And so moving on to the piecewise quadratic method, we will focus first on the CPU results. Shown in the graph are the interpolated values in blue and the actual values in orange or red. We'll skip past this quickly, but here's the implementation in MATLAB code. And as you can see in the graph, the interpolated and the actual values for the first half of the data, so 1982 up until the mid-90s, for that portion of time, the trend or the difference in the two types of data, the two plots, were not very large. So those were omitted from the error study just so they didn't skew or corrupt the data somehow. So instead, for this particular method, we decided to stick with the more active half of the graph, the plot, and take 6 even interval data points to compare interpolated versus actual values. And so the values are shown in the table below, but root mean squared error of 1700-ish, which is a bit higher than the cubic spline variant, and average percent error of 56%, which is also slightly higher than the CPU or the cubic spline variant. And in the GPU side of things for the same method, the blue line represents the interpolated values, the orange line represents the actual values, and similar scenario, we will skip past this quickly, but here's the implementation. The points tested for error were cut down to just those 6 even interval spaces to omit the relatively same valued interpolated versus actual values on the other half of the plot. But the RMSE value here is 2000, which is quite a bit less than the GPU variant of the first method. However, the average percent error is slightly higher than the cubic spline variant as well.
All right, and we wanted to compare the CPU versus GPU graphs to see how they would compare and maybe make any conclusions there. And we did make the conclusion that GPUs may be outperforming CPUs now and in the future. You can see GPUs in the interpolated cubic spline graph. It seems to be starting lower at CPU, or starting lower in the early years, and over time and around 2007 or 8-ish, the GPU seems to have gone past the CPU line, and it's really only time will tell if we can see how that may play out in the future.
Likewise, for the piecewise quadratic method, the comparison of the interpolated CPU and GPU values is shown here, and the trend seems the same, which is fair.
All right, and just a little bit more about the exponential regression. This is how we represented Moore's law. The curve fitting app used in MATLAB showed us the equation shown in the bottom left. And just as a small conclusion here, we can see that it's possible CPUs may be being dropped off of Moore's law in the future. You can see towards 2010, maybe a little later, CPUs have started to fall off a little bit and maybe not follow that line quite as closely.
And so with this project in mind, we would like to consider a few things for the future if we were to continue it. For example, we would like to consider what would happen if we were to use other methods. For example, the polynomial least squares approximation. There's a chance it could fit our data better and give us a better interpolation with which to work. We'd also like to see what would happen to the results if we would use 3 times or 5 times or an arbitrary number of data points compared to our original data. And we would also like to see what would happen if we were to focus on a subset of the companies represented in our data set. For example, if we were to just compare AMD, Intel, and NVIDIA. And finally, for the future work, we would like to consider as well whether or not we could predict the future trends in transistor counts using these methods.
All right, and just a little bit more about the conclusions we drew from here. We may require some more RMSE values from other exponential data sets. It seems like exponential data may produce high RMSE values, especially with our methods. You can see they were in the thousands. Graphics processors appear to be outpacing computer processors. This is again from the graph. We can see that the line for the GPU data seems to be trending higher in recent years. Moore's law seems to be breaking down over the past few years. So this may be attributed to the physical limits of our chip architecture. However, that may still hold. It's possible we may have new technological breakthroughs that may push our transistor counts above the line again. And over time, we can only see that. We also noticed that the natural cubic spline is slightly more accurate than the piecewise quadratic interpolation, at least with our data anyways. The spline seems to normalize the data, while the piecewise quadratic follows the curve more closely. We will, however, say that we wouldn't recommend either interpolation methods for our data set. It's possible, again, with the exponential data that the error seems to be way up, and it's even possible because our data swings so much over the years that may also skew our error calculations. But we recommend maybe using a polynomial least squares approximation or even an R cubic spline to see how those would work instead.
And that concludes our presentation. Thank you for watching.
Thank you.